Welcome. Today we look at Unit 13, Polynomial and Rational Functions, and we are at Day 3, the graph of a rational function, 5.4 from the book, and we will look at Objective 1 of graphing a rational function. There's a lot to graphing a rational function, so look at these 11 points. What you need to know when graphing a rational function. Don't worry, you don't have to memorize all of these steps. In the problems that you'll do from this section, it'll step you through each step individually, so you'll just answer them as they go. So if you had a function like this guy, you would step through all these things and try to figure them out, and then by the time you get to 11 at the very end, you should have a good idea, roughly, of what the graph looks like. There's something I need to talk about. It is the whole truth about factors. Sometimes the graph of a rational function will have a little hole in it. So it's not a vertical asymptote, it's not a horizontal asymptote, it's just a little hole in the graph. Here's how this happens. So consider this function x minus 2 over x minus 2. What does that look like? Well, for the most part, if x is any number except 2, let's say if x was 5, and I plug in 5 for x, I get 5 minus 2 over 5 minus 2, that's just 3 over 3. Oh, that's just 1. So if I plug in 5, I get a value of 1. Let's say that's a height of 1 there. And if I plug in 4, I'll get 1. And if I plug in 3, I'll get 1. Or if I plug in 0, I get negative 2 over negative 2, which is 1. And in fact, if I plug in any number in the world, I get 1, except there's just one exception to that, is that if I actually plug in 2, that's where the function's undefined. So there's a little hole right there, but otherwise, the graph looks like a nice horizontal line with height 1. That's kind of curious, right? That you can have a function with a little hole in it. Take a look at this graph, Q. So for the most part, this looks like x squared, because for any x that I plug in except for 2, the x minus 2 over x minus 2 cancels out. But if I do plug in a 2, then the function is undefined, so I get a little hole there. In general, the graph of, let's say, this function p of x, where I have a factor x minus a over x minus a, it looks like the graph of p of x, kind of like I have the graph of x squared, but with a little hole at x equals a. Now, even a little bit more generally, let's say I have some exponents on that repeated factor. There's a hole if the n is greater than or equal to the m. So there's more factors on top. And when I cancel those common factors, it'll end up clearing the denominator. However, if the amount of the factors in the numerator is less than the number of factors in the denominator, that's when I have a vertical asymptote, when canceling leaves a factor in the denominator. Here I have a few examples. So I'll ask whole, vertical asymptote, or neither. In this first case, when I reduce, I end up with x squared over x plus 1, which looks perfectly normal. So in this case, there's a hole at x equals negative 1. How about the next example? Well, x minus 7, and that's repeated. I'm left with x plus 3. So the denominator has canceled entirely, so I know that it's not a vertical asymptote, it really is a hole. And otherwise the graph looks like x plus 3. And in my last example, I don't see any repeated factors there, right? Oh, but maybe I have to factor the top. And when I cancel, I'm left with 1 over x plus 4. So it looks like there is a vertical asymptote at x equals negative 4. When x is greater than negative 4, it looks like the value of this thing is positive. And when x is less than negative 4, it looks like it's negative. So maybe the graph looks something like that. All right, so I'm going to go through two long-ish examples. We'll go through all of these steps, and we'll see what a rational function looks like. Here's our first example. We'll look at 3x minus 6 over x squared minus 25. Number one, let's factor the numerator and the denominator. So in the numerator, it looks like I can pull a 3 out, and with x minus 2. And in the denominator, x plus 5, x minus 5. So the domain is anything except where the denominator is 0. Well, it looks like the denominator becomes 0 at 5 and negative 5. So the domain is going to be the set of all x such that x does not equal 5, and I'll just put a comma, -5. So x is not 5 or -5. That's how we might write that. Number 3, now let's express this in lowest terms. Let's cancel any common factors. Well, in fact, I don't have any common factors. On the previous slide where I was talking about holes in a graph, sometimes we had factors on the top and the bottom, but in this case, nope, it's already done. It's already expressed in lowest terms. Already reduced. Number 4, let's find the x and y intercepts. To find the x-intercepts, I look at the reduced form of the fraction, and I look at where the numerator is 0. And it looks like it's 0 in this case when x equals 2. That's the only place. So that's the only x-intercept. How about the y-intercept? Another name for the y-intercept is simply r of 0. So what happens when I plug in 0 into the r function? So 3 times -2 over, I plug in 0 for x, -5, plug in 0 for x, 5, looks like -6 over -25. They're a beautiful number, 6/25. Okay, so maybe it's not the prettiest thing in the world, but there it is. That's my y-intercept. So thinking about the graph of this thing, the graph of the function crosses the x-axis at exactly one point, the point 2. And it crosses the y-axis at exactly one point, this point 6/25. All right, so now we know where this function crosses the two axes. Moving on, number 5, let's describe the behavior of this function at the zeros. Does it cross or does it touch? The way I determine that is, again, by looking at the numerator and looking at multiplicity. This numerator, where it's 0, that has multiplicity 1. Something has multiplicity 1, that's when it crosses. Now remember, odd multiplicity means that the graph crosses. Even multiplicity means that the graph touches. So in this case, it'll just cross. Cross at x equals 2. Now let's look for the vertical asymptotes. Vertical asymptotes, those are going to occur where my denominator is 0. So at -5 and +5. And 7, let's describe the behavior. Now, we can have asymptotes where the graph splits, so something like this, or we can have an asymptote where the graph sort of stays together, something like this. And the graph will split if the multiplicity of that 0 is odd, and it will stay together if the multiplicity of that 0 is even. When I look at my fraction here, the multiplicity of x minus 5 is 1, which is odd. And since it's odd, that means that it splits. And the multiplicity of the factor x plus 5 is also 1, so that means that the graph will split at that asymptote as well. This first factor talks about the x equals 5 asymptote, so it somehow splits. Now, I don't really know if it splits like that or if it splits like this. It could be either way. I need to do a little more analysis, but I just do know that it splits somehow. And same thing at the -5, so they both split. So there we go, split at both. Next one, number 8. Let's identify horizontal or oblique asymptotes. So for this one, we need to look at the degrees of the top and the bottom. So let's expand it all out. So I get 3x minus 6 all over x squared minus 25. That's what we had originally, way up on top. And what do you notice about degrees? It looks like the top has a degree that's smaller than the degree on the bottom. So since the bottom has higher degree, this has a horizontal asymptote at 0, which is actually just the x-axis. So this whole x-axis itself acts as a horizontal asymptote. All right, so the horizontal asymptote is y equals 0. The next part is a little bit new. We haven't done this before. It says, find where the graph crosses the horizontal or oblique asymptotes. So to do that, I'm going to set my function equal to the value of the asymptote. So this, in this case, y equals 0. So I'm just going to say 0 like that. So where does this graph equal 0? Well, let's multiply both sides by x minus 5, x plus 5. That just becomes 3. X minus 2 equals 0. And the only way that this works is if x equals 2. So that's where it crosses. cross at x equals 2. That should make sense also, right? Because that's the only 0 that I have of this function. All right, number 10, let's identify the intervals where my function is positive or negative. Now the trick to this is I need to look at all the zeros and asymptotes. And these are the only places where the function can change from positive to negative. One thing that we can do is we can test at various points. Let's take my function. What if I plug in a number that's really, really big? 100. If I put 100 in for x, is that number going to be positive or negative? Well, 3 times, that's like 98. Okay, so that top is positive. And 100 minus 5, that's positive. 100 plus 5 is positive. So actually, if I plug in 100, everything becomes positive, so my answer is positive. So I actually know that to the right of 5, the answer is positive. Now, I could do the same thing for picking a number between 2 and 5. I could put 4 into this function, and then I could put 0 into the function, or negative 8 into the function, and test each of these various regions. But I can also use information about the asymptote. So I know that the asymptote splits, and I know that there's a horizontal asymptote, so the graph probably looks something like that. And then it splits, and so it comes up from the bottom. And then I have a 0 here at 2, so it comes up and it must cross at 2. So the graph must be negative from between 2 and 5. Now, does the graph ever cross the x-axis again? No, it probably looks like it goes up. It has another vertical asymptote, so it's positive here. But I know at negative 5 it splits, so it's going to come up and be negative over there. So I can say, for these various regions of the graph, whether the graph is positive or negative. So I kind of draw out a little x-axis and I identify where it's positive and negative. Well, now we're actually ready to graph. Here's the basic information. I have my axes, I see my asymptotes, I see the point where the graph crosses, and like I was analyzing before, I know it comes something like this, and then I have a vertical asymptote that comes up from the bottom, crosses through 2, but then has another vertical asymptote there. It splits, so it must come up from the bottom, and then use the x-axis as a horizontal asymptote there. All right, at this point, I recommend pause the video and review all the steps here. Make sure that everything makes sense. See how we got to this place. Okay, I have one more example. Example number 2, and this one's a little bit trickier, but some of the parts are the same, so I'll go through this a little more quickly. Number 1, let's factor the numerator and denominator. It's actually mostly factored already. This guy here on the left, that factor, that looks like it can be factored even further. Now the one thing is I have a common factor of x minus 4 on the top and the bottom. I didn't have that before, but for step number 1 right now, we can leave it like that. That's the factored form. All right. Tell you what, problems number 2 through 7, you can do those. Give those a try. You can do it. So pause the video for a few seconds. Well, pause the video, and then for a few minutes, try the problem on your own. And then start the video again when you're ready to check your work. All right, let's see how you did. Here are those solutions. Pause the video again, and really look at those answers. See if they match up with what you expected. At this point, let's continue on. So let's take a look at number 8. Identify the horizontal or oblique asymptotes. To do this, we need to fully expand out the function. So I'm going to take this reduced form and I'll expand it out. Here we go. At this point, now that it's been expanded, I see that my numerator has degree 3, denominator has degree 2. The degree of the numerator is 1 more than the degree of the denominator, so it must have an oblique asymptote. Let's find that oblique asymptote. So I chop off stuff after the first 2 terms. Then I can cancel common x's. And now multiply times the conjugate of the denominator. Use FOIL. And that becomes, when I expand through, and now we chop. And then cancel common x's, and I'm left with x plus 10. So that is actually the equation for the oblique asymptote, x plus 10. I know it's kind of a lot of work to get these oblique asymptotes. I promise you that you'll never get anything more complicated than this. In fact, I think the ones on homework are pretty much easier than this. But it's good to know how to do them for these tougher problems. Okay, I've got the oblique asymptote. Y equals x plus 10. Number 9, now let's find where the graph crosses the horizontal or oblique asymptotes. So what I'll do is, I'm going to set my function equal to the asymptote, and now I just need to solve this equation. That's all I need to do. So this is a little bit more involved than any of the homework problems, I promise. So in fact, at this point, if you've been rigorously taking notes, I promise you don't have to take notes on this next part. Just watch what I'm doing, see that it makes sense. We'll get an answer at the end, and at least understand the process that I'm using to get the answer. All right, here we go. So the first thing I'll do is multiply both sides by this denominator. Now let's expand both sides. To expand this side, I do a nice trick. I'm gonna distribute the x first, and I'll distribute my x across the 3 terms, and then I'll distribute the 10, and distribute the 10 across those 3 terms. Here we go. Some of these terms combine. I have a minus 4x squared and a plus 10x squared. I also have a plus 4x and a minus 40x. But now look at this. I have x cubed plus 6x squared on the left, x cubed plus 6x squared on the right. I can subtract that from both sides. Add 36x to both sides. Divide both sides by 45. And 40 over 45 is the same as 8/9, which is really 0.8888 forever and ever. So what this means is that the point where my graph crosses the oblique asymptote has an x value of about 0.89. We'll just call that 0.89. So if that's the x value, what's the y value where it crosses that oblique asymptote? Well, y equals x plus 10, so all I need to do is add 10 to that, 10.89. So this gives me one more point that I know for sure on my graph. All right, so here it is. I cross at the x value of about 0.89, and it goes through the point 0.89, 10.89. All right, number 10, let's identify the intervals where my function is positive or negative. I know that the graph has an x-intercept at -3, it has an x-intercept at 0, and it has an asymptote at x equals 2. So between those points, that's when my function can change from positive to negative. Well, let's do this trick again. I'll plug in something very positive into my function. If I put 100 into there, is the answer going to be positive or negative? And in fact, it turns out to be positive. I'll have a positive number divided by positive. So the graph starts on the far right in this region above the x-axis. Well, it has a vertical asymptote, and it doesn't cross the x-axis. I don't have any other zeros. So somehow, the graph must go up onto that vertical asymptote. Oh, but what do I know about that vertical asymptote? The two sides stay together, so it must come down on that side. So I'm positive to the right of the 2, and I'm positive between 0 and 2. Now at 0, does the graph cross or touch? It crosses, so it will cross at 0, but now it's going to touch another point at -3, and it touches, but doesn't cross, and then it goes down. So I have negative in this region and negative in that region. So ignoring the actual graph part, I know that my function is negative, negative, positive, and positive between the points that really matter, the zeros and the vertical asymptote. So there we go. We have our little picture to demonstrate that. And now let's graph it. And don't forget the hole. I know we haven't talked about that since the very beginning, but there's a hole in there somewhere. I've drawn the basic information here. There's a 0 at -3, a 0 at 0. There's a vertical asymptote at 2, and there's an oblique asymptote, y equals x plus 10. So it's not to scale. This has a y value of 10 right there. Starting from the right, at the asymptote, I know the graph was positive here, so in fact it has to have a look something like that, since it gets really close to the slant asymptote and it gets next to the vertical asymptote, and then it's going to come down on the other side. They stay together. Oh, but where will it cross? This graph will cross that slant line, and it's going to cross at this point, 0.8, 10.8. So somewhere right around there maybe. Okay, so it crosses that, and then I know that it goes through 0, it goes through the origin. Okay, and then it must come back up and just touch at -3, and it comes back down, and then it must try to reach that slant asymptote again. So our graph roughly, very roughly, looks something like that. All right, and the one thing that remains is the hole. Don't forget the hole. The factor that was common to the top and the bottom was x minus 4, so it looks like at x equals 4, there's a hole. So let's make a 4 there, and I'll put a hole right about there. There we go. That's a reasonable approximation for the graph of this function. I know it's a lot of work, but it's all right. You know, these things get easier as we do them more, and I promise, like I said before, you won't have to do any calculations as difficult as what I did when you figure out your slant asymptotes. All right, look over this information here. See that it makes sense, and see that you can do this on the homework too. All right, I'll stop there.